Welcome, geometry students. Today we're doing 5.3 bisectors in a triangle. Getting close to the Christmas holiday, so hope you guys are having a wonderful time so far. Let's get started. So the first vocabulary word we need to understand before we begin this section is concurrent. What does that mean? Well, concurrent means happening at the same time. But in math, really what we're talking about is in the same place. Same location. Okay, so a point of concurrency is where two or more lines meet. Okay, so a point of concurrency happening at the same time. So where they're happening at the same time is where they meet. Now, our first theorem of the day, concurrency of perpendicular bisectors theorem. Okay, so if it's talking about concurrency, it's talking about where one or more things meets. And if it's talking about perpendicular bisectors, we know what that is. It's a line that is perpendicular to another line. That means it forms 90-degree angles. And it bisects another segment, meaning it splits it into two equal parts. So we're looking here at triangle ABC. Oh, here's vocab. Perpendicular bisector. Almost missed it. That is a line that forms a 90-degree angle and splits a segment in two. Into two equal parts. How about into congruent parts? I like that. All right. Now, so we have this set up for us. Now, what we're going to do is we're going to create perpendicular bisectors where? Well, if we're bisecting, that means it needs to be at the midpoint. So if we're looking here at AC, the midpoint is right here. Okay, so now what does this need to be? Well, this needs to be 90 degrees from this line. Now, this is always, year after year, this is always a common question. Well, how do you know what's 90 degrees? Well, unless you have a protractor, we're not measuring it exactly. We're just giving like an estimate. And I don't mean estimate is that this is not an exact science. You could actually find the exact line that bisects it. You could measure it, okay, and make sure it's equal on both sides, and then measure its 90 degrees. But for this purposes in the notes, we're giving it our best guess, okay, because I don't know if that's actually 90 degrees or not, just to demonstrate the principles, okay, because something happens at the point of concurrency of perpendicular bisectors, and that's what we're going to talk about, okay. Now, the second midpoint, so if AB is over here, so we're going to form this to be 90 degrees. Okay, so something like that. Okay, and again, it's not exact. I know some of you might be yelling at your screen. Okay, but now we have BC, and we're going to form a perpendicular bisector like this. Okay. Now, I did an okay job, not terrific, but not bad, at getting these all to meet at the same spot, because that's what it's all about. Concurrency, all at the same spot. Where do they all meet? They all meet right about, I'm going to make this dot big so you can't see my mistakes. There you go. So that's where it meets. That is the, now let's label it, that is the point of concurrency. Okay, where the lines meet. Now, what are special about these point of concurrency? Well, we've already said that it's perpendicular bisectors, so these are split into two equal parts. Okay, it also forms 90-degree angle with these segments. But also notice how it doesn't necessarily need to go through any specific point of the triangle. Notice how it doesn't touch the vertices at all. Okay, so nothing goes through the vertices. And that's something just to keep straight some of these other theorems that we're talking about. Okay, so that's the point of concurrency. Now, something special happens at the point of concurrency. Well, let's take a look. Well, what happens is we can create a circle around the triangle, and the point of concurrency is a special place. To kind of demonstrate this, what I'm going to do is I'm going to draw a circle around this guy. Okay, so I'm going to draw a circle, and I'm going to touch the vertices of this circle to each one of the vertices of the triangle. Did I say that right? What I really mean to say is we're going to make the circle touch the edges, the points of the triangle, okay? So I did that. Now, what do you notice about the point of concurrency? And again, this isn't exact because my circle's a little off and this and that, but what do you notice about this point of concurrency here? Now, hopefully what you'll notice is that this is the center of the triangle. So the point of concurrency is, okay, I'm going to draw an arrow over here. It is the center of, did I say triangle? I meant circle. That is the center of a, and this is a special word, circumscribed circle. Okay, circumscribed means to go around. Circumference is to go around. Okay, so circumcenter of the triangle is the center of a circumscribed circle on a triangle. Okay, what does that mean? Well, it means that this point of concurrency, POC, is also the center of a circle that you draw around the shape. So it's kind of obscure, but at the same time, it's very interesting that this happens. Okay, now, besides just being the center of the circle, there's also something very important about this point of concurrency of the perpendicular bisectors. Okay, so we could draw our perpendicular bisectors here like we did above, but I'm not going to do that because I want to demonstrate something else that's important. What's important about these points touching the circle and then the center of the circle being there where the lines meet? Well, we could draw these lines here like this, okay? And what are these lines called? The center meeting up with the outside of the circle. What are those called? These little lines. These are radii. So this is a radius. Okay, so this is a radius. This is a radius. It's the same distance. It's the distance from the center to the edge of the circle. And this is a radius. What do you know about the radius of a circle? It's the same no matter where it is. Okay, on the circle. So if I draw this, oops, I'm trying to get this to swing around with me. Hold on, give me a moment. Okay, so if I draw this like this, it is the same distance all the way around, okay? That's the cool thing about a radius. So if I look here, and I draw these same, I might want to change the color a second, just because I want to make it lighter. So I'm going to change the color. Bear with me. My pencil's being funny. All right, style. Let's go this light pink. Okay, so I'll make it light pink. Now, if I draw these same light pink lines up here, what happens? Well, it's the distance between the vertex and what's called the circumcenter. Okay, so let's kind of give a recap. There's a lot of things happening. Number one, we drew 3 perpendicular bisectors and they all met up at the point of concurrency. This point of concurrency also happens to be the center of a circumscribed circle. So we draw a circle around the triangle, and at that same point of concurrency is the center of that circle. Now we can draw radiuses, radii, from the center of the circle, the point of concurrency, to the vertices of the triangle, and we know all those lines are the same distance away. So this was a long way of saying that the circumcenter of a triangle is equidistant, that's an I, equidistant from the vertices of a triangle. Okay, so any triangle that you draw, okay, and you draw a circle around it, that center of that circle will be the same distance away from the 3 vertices of the triangle. I think that's pretty cool. So that is the circumcenter of the triangle. Circumference, that means to go around. Circumcenter, draw a circle around. And the center of that circle will be the point of concurrency of the perpendicular bisectors. That's a lot to understand all at once. Go ahead and pause that, rewind, take all of the time you need. But when you're ready, let's start example 1. Okay, you're ready. Let's start example 1. Where in, on, or outside the triangles below are the circumcenters? Okay, a couple different strategies we could use here. We could, and this is kind of like not using your protractors, okay? So giving it your best estimate. What we could do is we could measure the midpoint of each one of these triangles. So you measure it and you divide by 2, and then you measure that distance, and that's the midpoint, okay? So then it would look something like these are equidistant, these are equidistant, there we go. And then we could get our protractor and measure this to be 90 degrees, okay? Make sure that's 90 degrees, make sure this is 90 degrees. Okay, that looks to be about 90 degrees. No, probably more a little bit like this. Okay, so more like this. That looks like 90 degrees. And then we have this guy go 90 degrees. Okay, so 90 degrees, 90 degrees. Now we have the perpendicular bisectors, okay? So I would know that this is my point of concurrency. For acute triangles, it's always inside the triangle. The POC is inside. Why am I putting that parentheses? Not sure. I'll put POC inside. Now, another way to double check this. This way is, I think, easier. We draw a circle around the triangle. Okay, draw the circle around the triangle. And move it into position. That's close enough. Is it though? There, that's better. And the center of that circle is exactly where the point of concurrency is. Now, right triangle, let's take a look at this guy. If we draw a circle around this guy, okay, I messed up a little bit. Hopefully it's not too bad though. Okay, let me move him over just about there. There, okay. That doesn't look right. Okay, again, I'm not using exact science here. The best thing to use would be a compass to draw this, but you're getting the general idea. I'm not happy with it. I'm sorry. I just need to adjust it a little bit. Right about there. I think my problem is the circle's too big. There. Okay, that looks good. Now, the same thing. We could, now, actually this one's not the same thing. It's a little bit different. So if we were going to connect the midpoint, okay, so we're going to go midpoint here, midpoint here, midpoint here. Okay, and we're going to go this way. Okay, we're going to go this way. Okay, 90 degrees, 90 degrees, bisected, bisected, and then bisected. Where does it meet up? Well, it meets up on the hypotenuse. So for a right triangle, the POC is on a side. And more specifically, it is on the midpoint of the hypotenuse. So on the midpoint of hypotenuse. Okay. And as we draw the circle, we notice that, again, it's the same distance. This point is the same distance away from the vertices. I'm going to use this light pink again. Okay, so this is the same. That's a radius. This is a radius. And this is a radius. So that actually makes the hypotenuse a diameter because it's twice a radius. Okay, so that's for right triangles. The hypotenuse is the diameter of a circumscribed triangle. The point of concurrency is the center of that triangle, okay? Now, obtuse, I'm not going to do the, well, I guess I could. Real quick, I'm going to draw the little lines here that demonstrate the perpendicular bisectors. It's going to look something like this. This is the one that's kind of tricky for most people. Okay, as you draw this bisector, it's going to look something like this. Okay. 9 degrees, it has to meet up outside the triangle. So with an obtuse triangle, the point of concurrency is outside the triangle. And if you take a look here, it makes sense why. If you draw a circle, it's a big one. Okay, so I messed up the circle already. Okay. Oh, good, I got it. Okay. So we have to draw the circle, and as you can see, we draw that circle. It's pretty large. And actually, I'm not doing a great job of... Oh yeah, I'm not touching all the vertices, no wonder. I was like, why is this circle so small? I have to make this pretty large to touch all the vertices. Okay, so I have to extend it this way, I have to extend it this way. I even have to move it. So as I move it, you can see that this line is getting closer and closer to the center of this circumscribed circle, okay? So done with example 1. One more example to go, bear with me here. So where is the circumcenter? So as we're doing this, the first thing we have to do is we have to find the midpoints. So we have to find the midpoints. And honestly, we only need to do 2 sides. If it meets up with 2 perpendicular bisectors, it's going to meet up with the third. So find midpoints of 2 sides. So you can kind of use your own strategy here, but try to pick the sides that are easiest to find the midpoint of. If you want, you can re-look at the midpoint formula, which is this. You find your XM and your YM, and that's your midpoint. Okay, so your XM is going to be X1 plus X2 divided by 2. This is just a quick reminder. Y1 plus Y2 divided by 2. Okay, but if I'm looking at this guy, it's going to be pretty easy if I'm looking at this particular side. Okay, so I'm going to thin this up a little bit. If I'm looking at this side, the midpoint is just going to be halfway between, which is going to be 0, 3. Okay, that one's going to be pretty easy. You can just count it on the line and find the mid distance here. And this one, same deal, should be pretty easy because it goes to 4 and the y values don't change, so this is going to be 2, 2, 0. Now, we have to draw. So step 2, this is actually the difficult part. We have to draw perpendicular lines from the midpoints. Okay, and that usually means we have to find the equation with a perpendicular or opposite reciprocal slope. These problems can be very complex. I mean, they can be very complex depending on the level that you're going to. Right triangles are the easiest because the equations are rather simple, but be prepared for equations that take a lot of time to solve, okay? So it looks like I didn't exactly put it in the midpoint. I'm looking here and it's looking like it's not going to line up perfectly, but it's going to be close. That's a little rough. Looks like I need to move that up and that one over. So I'll go ahead and do that just to make sure this is a little bit better. So I'll say this is the midpoint and that's the line, and then I'll say this one is a midpoint. That's pretty close. We'll count that. So here we have our point of concurrency. Okay, that's our point of concurrency. But here's the problem. Where is that? Where is the circumcenter? Step 3 is we need to find the intersection. Sorry, my pencil's again going a little haywire. Find the intersection of the two of, we'll put two, I'm going to write the two perpendicular bisectors. Okay, usually that involves solving a system of equations. Okay, so again, this could be very complex, like I said, with certain problems, solving system of equations, but with right triangles, it's very easy. Now, why is it very easy? Because we found out earlier that for right triangles, it's on the midpoint of the hypotenuse. So one thing to do is just be to use the midpoint of these 2 points, okay, which I'll try to show in just a second. But I want to show that this line right here is the perpendicular line. It's a vertical slope, so it's in the form of x equals 2. This is a horizontal line, so it's in the form of y equals 3. And so obviously our POC is going to be at 2, 3. Now if you wanted to do the midpoint way with these problems, we can go x1, y1, x2, y2. Okay, so we have our x1, y1, x2, y2. And if we plug these in for x1, we get 0 plus 4 over 2. And then for our y's, we get, what's that, 0 plus 6 over 2. I know I didn't put that right order, but you understand me. So we get 3 and we get 2 for our x, and that's why we get xm, ym, 2, 3. So that's just another way of finding 2 different ways to find the circumcenter of a right triangle, which this one is, find the midpoint of the hypotenuse, or to find the intersection of those 2 lines, and that is how you do it. I know this is a lot all at once. Take your time. There's going to be some follow-up videos with some CUDA tutorials, so make sure you guys watch those, and make sure you guys stay tuned for part 2 coming up right after these messages.